Okay. So we've been talking about ways to describe a function for several days now. So we've talked about domain and range. We've talked about positive, negative, 0. We've talked about increasing, decreasing, and constant. We've talked about the extrema, that's the mins and maxes. And then we've talked about end behavior. And the last topic that I want to talk about here in regards of ways to describe a function So the last one is going to be as a transformation of a parent function. So there's a bunch of vocabulary in here that we need to kind of dig into and make sure that we really kind of explain to give us a good notion of kind of what we're saying here. Because just these words on its own probably don't give us much indication of what I really mean here. So let's start with this idea of a transformation. Recall from geometry last year, you guys talked about transformations in geometry. The types of transformations you talked about were translations, so if I had a shape in the XY plane and I just moved it over to a new location, but like the shape stayed the same, the size stayed the same, and the orientation stayed the same, that's a translation. For example, like if you moved it right, 4 units or something, is an example of a translation. If you're just picking the thing up and just sliding it up or down or left or right or some combination of up and down and left or right. Does everybody remember that piece of vocabulary from last year? Okay. So another type is reflection. So again, if I take that same triangle and say I reflect it across the x-axis, I get something like this, correct? Where the shape and the size have stayed the same, but the location has changed and possibly the orientation changed as well, right? Notice my triangle is pointing down after the reflection. So the direction could have changed as well. Everybody kind of remember that one? Okay. The next one is called a dilation. So for a dilation, you're noticing that the shape is changing, or the shape does not change. The size changes. The location might change, but the orientation should stay the same. Notice it's still pointing in the same direction. Everybody recognize these from geometry when we talked about geometry last year? There's a fourth one that you probably mentioned that is not really applicable for this algebra course, which is called a rotation. We're not going to worry about those, so I'm not going to bother mentioning that one. But you probably talked about it in geometry briefly. And the reason that we don't worry about that one is that to actually apply a rotational change to a point involves mathematics that you haven't learned yet and aren't really relevant to this course. It's a trigonometry concept that you need, which is beyond the scope of what we're doing here. So, everybody's okay with this idea? Okay. So, if we're, say, taking a single point here, let's call that point just generically xy, and I moved it to the right 4 units, what coordinate is going to change on that point? The x-coordinate or the y-coordinate? The x-coordinate. How much is it going to change by? It's going to go up by 4, right? Everybody agree with that? So these translations are just going to be adding or subtracting to the x or y coordinate. So we're going to be adding or subtracting to the x or y coordinate, or both, right? If we were going like left 4 and up 7, like that's still a translation. You can do a different amount to each of them. Everybody's okay with that idea? So let's kind of think the same way. So let's say here we have, again, the point xy. When I do that reflection, how does that xy change? What coordinate changed? The y coordinate. Good. And how did it change? It just becomes negative. So to do a reflection, we're going to negate the x or y coordinate. So in the case of here where we reflected across the x-axis, which one did we negate? The y. Which one do you suppose we'd negate if we reflect across the y-axis? The x. So it's always kind of the opposite coordinate of the axis that you're doing the reflection on. Everybody okay there? Yes.
Is there a function across the y-axis? So like the right side of the axis, wouldn't it be? Like, yeah.
So, well, if this was like -2, this would become negative of -2, which would be +2. So you're still doing the negation. So if you negate a negative, you end up with a positive. But yeah, you're absolutely right. Oops, and I meant the x coordinate or whatever. Sorry. That was confusing. Is that okay with that, Chloe? Okay. Yes. Of course. All right. So for a dilation, again, let's pretend that we have an x or like a point in xy. When I do a dilation, how is that? How are those x and y affected? Yeah, they'd be multiplied by something, like if it's a factor of 2, they would get multiplied. Now, my suspicion is in geometry, it's been a while since I taught that course, when you talk about dilations, you only talk about dilations that are applied to both the x and the y. Did you talk about dilations applied to one coordinate or the other? I'm guessing probably not, because you lose the similarity argument, which I think is where that's packaged in, is you talk about similar figures kind of at the same time as dilations. And if you don't do the dilation like symmetrically, you lose the similar figures. In algebra, we can do that. Like, there's no reason you can't just like dilate the x coordinate or just dilate the y coordinate or dilate them different amounts. Just to be clear, they don't have to be the same to still be a dilation. Okay. All right, so everybody kind of remember this just as a light review from geometry. These same concepts are going to apply now algebraically. So remember that a function is just a set of x or a set of ordered pairs, right? Everybody remember that? Okay. And remember that we can represent a function with like a function notation. Everybody okay here? So f is some generic rule. So if I change the y coordinate, I could multiply the y for my dilation or my reflection, right? Because if okay, let me pause here for a moment and go back. Let me start. I'm going to get back to there. I want to do something in between, though. I think it'll be a little bit more clear as to where I'm going with this. Okay, so we have some point, right? And what I want to do is kind of create a description for any of these transformations I can do to that point. Everybody's okay with that idea? So if I want to translate the point left or right, I would need to add or subtract some number from that. Everybody agree with that? Okay. I'm going to write it as a subtraction. And similarly for the y. And I'm going to pick the letters H and K to represent any kind of number I could use there. So like if I'm going left 2 units, I would use -2 or whatever. Everybody's okay with that idea? And similarly, if I wanted to do a reflection, I would multiply by -1 to the x or y coordinate. Everybody agree with that? Or if I want to do a dilation, I would have to multiply by some number to the x or y coordinate. So I'm going to package those things together. So I'm going to package them together in this way. Oh, come on now. Stupid machine. Okay. So, if I wanted to think about this instead as x comma f of x, remember we talked about function notation when we reviewed. And function notation I can use interchangeably with a y. Y equals and f of x equals. They're really saying the same thing. Do you guys remember we talked about that briefly here? So I can start with y equals f of x. So in place of y and x, I'm going to use these transformed coordinates. And if I'm going to graph something, usually I like to have that y coordinate by itself, right? If I'm going to talk about a function, I usually write it as like y equals yada yada yada, where the y is all by itself. So I'm going to go ahead and do that. I'm going to multiply both sides by a, and then add k to both sides. going to pause here and let everybody kind of finish writing, and then we'll talk about really what we're saying here and explain this in more detail. So what we're seeing here is that the A and C coefficients control two things. They control whether a reflection has taken place, or they control if a dilation has taken place. So depending on the magnitude of that A and the C, it's going to depend on whether that dilation is happening in a stretching motion or in a shrinking or compressing motion. Yes, Grace? That's the absolute value of C? So, if I look at the first three lines here, they're all related to C, right? First thing says if C is negative, then we reflect across the y-axis. If the absolute value of C is greater than 1, then we have a horizontal stretch. And if the absolute value of C is less than 1, we have a horizontal shrink. So C can tell me three pieces of information, right? Whether it's a reflection or a dilation. Because remember, what is C doing if we went all the way back and looked? C is multiplying the x-coordinate, right? Which is what happened when we do dilation and when we do a negation, right? Those are both things that happen to the x-coordinate. So that's what C is doing. Now we have to write our rules a little bit carefully. The sign of C, whether it's positive or negative, controls the reflection. And then the magnitude of C, how close that value of C, or the absolute value of C is to 1, controls whether it's a stretch or a shrink. So numbers that's magnitude is bigger than 1, things like 2, negative 2, 3, negative 3, 1.7, negative 1.7. Any of those values that have absolute values bigger than 1 cause stretches. Things that are smaller than that, like a half and negative a half, 0.6, negative 0.6, 1/3, negative 1/3. Any values like that whose absolute value is less than 1 will cause the shrinks. Okay, with that idea, we'll get to how we apply it here in a moment. So if you're still looking for the payoff, it's coming. We just have a little bit of foundation here to lay. notice similarly, the A does almost exactly the same thing, right? What did the A do if we went back and looked? The A is being multiplied to the y coordinate. So the A is going to do the same kind of thing, but it's going to do it to the y coordinate. So again, if the A is negative, it's going to cause a reflection. And depending on what the magnitude of that A is, how close it is to the absolute value of 1, will determine whether it stretches or shrinks that coordinate. Now the H and the K's are just translations. So if the H is, I don't know why I put absolute values here. Those do not need to be there because absolute value being negative makes no sense whatsoever, right? Yeah. Don't know. I got going. And sometimes you just make mistakes when you get going. Good. The point is, though, that I caught it. Okay. So let's look at an example here. So if I want to describe the transformation occurring to f of x in this function, what I would go back to is trying to figure out whether 2 is this an A, H, or K. Oops, A, C, H, or K. Which one of those three coefficients is it? So if I look at my general form, it's out front of the f of x. So this tells me that 2 is my A. Everybody okay with that? If I go to my list of criteria, I'm going to look at the parts concerning A, which is these 3 lines here. The first line says if A is negative, then we reflect across the x-axis. Is A negative? No. So there's no reflection. Next thing, it says if the absolute value of A is greater than 1, then we have a vertical stretch. Is the absolute value of A greater than 1? Yes, right? The absolute value of 2 is 2, and that's certainly greater than 1. So we would say that there is a vertical stretch. So what that would mean visually is if this green was my original triangle, my new triangle might look like this, where it's been stretched vertically. Now, eventually we want to move away from thinking about these transformations in regard to shapes and want to start thinking about them in regard to functions, and we'll kind of move more in that direction tomorrow. But this is fine for today.